Hello and welcome to an introduction of the relaxation algorithm. I'm going to talk here first a bit about theory and explain some key concepts, and later we're going to look at a Mathematica notebook where we solve the Ramsey-Cass-Koopmans model with the relaxation algorithm. I would like to refer here to the main resource. It's Trimborn, Koch and Steger with their paper Multidimensional Transitional Dynamics, a Simple Numerical Procedure. So what I'm doing here in the theory part is basically just reframe their appendix. The appendix in their paper is where all the techie stuff happens. Sometimes I think the notation deserves some extra comments, so I figured I reframe it a bit. However, if you miss something, I think I've got everything important covered, but if you miss something, by all means check out the appendix of the paper. So the idea here is that we have a system of differential equations for n variables. Here again, capital N is taken from the appendix, notation is taken from the appendix, and will, whenever we can, be used also in the Mathematica notebook. So it's worth remembering the notation here. Now the relaxation algorithm attempts to describe the transition path from an initial state to a steady state. And since a lot of macro models are infinite horizon and also continuous time, we have to think of some smart way to work around this problem. After all, if we're trying to solve a system computationally, we rely on finite memory and finite precision, so we have to kind of work around this. And the way the relaxation algorithm works around it is that it cuts the time into a grid of time points. Here capital M is the number of time points. The larger M, the finer the net, basically, the more precise our solution will be, but of course also the higher the computational burden, the longer it will take to run. So the high-level intuition of this procedure is that we guess a path, we have an initial condition, we have an endpoint, and we have an educated guess, more or less educated, how we might behave towards this steady state equilibrium. And then what we do is we evaluate the system for our guess, get the errors, see how wrong we get it, and update the solution using a Newton-Raphson step. And this is repeated until we meet convergence. And to formalize this idea, let's talk about the function space. So the function space is as follows. So we have a couple of variables. In our Ramsey-Cass-Koopmans case, this is capital and consumption. Sorry, but it could be, the more complex the models get, the larger the vector of variables. But not all of these variables need to be affected by time. And this tilde notation is exactly here to capture this idea. So x tilde are all the variables that change, or that are affected by time, that change over time, that are dynamic, if you will. In principle, this could be the same as just x, right? X are all the variables that we have. There's nothing stopping us from saying x tilde is the same as x, and in the Ramsey-Cass-Koopmans case, this is actually the case. But in the more general setting, it doesn't need to be the case. So we have capital N equations, right? Not all of them need to be dynamic. And for notational reasons, we just say, okay, this function f here, this is the function that captures actually, okay, how do all the variables that are actually affected by time change over time? It's the derivative of this variable with respect to time. And then you see, okay, this function, right? Time is a real thing, is a real a variable, only in the positive real axis, and so these are the arguments of the function basically. This is time. It takes a positive real value. These are the variables, right? All the of dimension n, and we're gonna map it onto n tilde, which is only those variables that are actually affected by time. Of course, there are, if this is the case, right? If n tilde is smaller than n, and it can only be smaller, right? It cannot be larger. It can be smaller or equal. In the Ramsey-Cass-Koopmans case, n equals n tilde, but in general, it could be that n tilde is smaller than n. And in this case, that means we have some stationary equations. And in order to fulfill the stationary equations, we need to have also stationary conditions that need to be met by the stationary equations. So the conditions that x has to satisfy at any time. So in case only a subset of my variables change over time, then I need some extra conditions. And these conditions are denoted by g. This g is exactly, again, time here is the positive real line, x is exactly the dimension of my variable vector, and it's going to be mapped into n minus n tilde. So all those stationary equations. To simplify notation, we call the number of initial conditions n1, the number of end conditions n2, and the number of stationary conditions n3. So for all the dynamic variables n tilde, we need as many initial and end conditions. So together there need to be as many initial and end conditions as there are dynamic variables. And altogether there need to be as many conditions, boundary conditions in total, as we have variables to solve for. So basically this last row is kind of intuitive, not necessary for understanding what's going on basically, but if you're interested in the details, these are how the functions are defined. And so basically what you do is you set up a system of equations of n variables, so n equations, now you have n boundary conditions, and now we try to find the root, which is the solution of the system. Remember, we said we cannot do this for continuous time with the computer because we have limited storage and finite computer precision. But what we can do, and what the relaxation algorithm does, is we cut the time into a grid. And this is particularly useful for dealing with infinite time horizon models, as we typically have in macro. So what we first do is we map this positive real line, time can run from 0 to infinity. We map it into the unit interval starting from 0, ending at 1. So, and after this, we kind of have a finite time interval now, and this we can cut up. So what we do here is we introduce this time variable tau, because t is reserved for the running variable that runs from 0 to infinity. We now need a new running variable that goes from 0 to 1. And in this case, as the authors of the original paper also do, we employ this mapping from 0 to infinity to 0, 1. So basically saying that whichever t we plug in here, let it be years or whatever seconds, we get an associated tau to it, which is between 0 and 1. And if time goes to infinity, in the limit, tau will go to 1. Okay. So what we will now do is we change the variables from t to tau, which results in a bit of a different system of equation. So now we take the derivative not with respect to t, but with... And so having cut up time now, we made the problem digestible for a computer, because we overcame the infinite time horizon, remember, by mapping it into the unit interval. We made a transformation, a change of variable. That's the one solution, and then we still had continuous time, and now we cut up the continuous time in this unit interval into equally sized chunks, and now we have a discrete finite time horizon problem. And now we want to answer the question, okay, how do the variables of interest change over time, right? So in the end, we want to know how do the variables of interest change on their way into the steady state. And this is so exactly what we do here. So considering the time interval, let's say tau and tau k plus 1, so tau k and tau k plus 1, it's 2 consecutive time points, and the interval here is a continuous interval. So how did the variables of interest change? Well, that's exactly that. So the value of the variables of interest at the end of the period minus the value of the variables of interest at the beginning of the period is the change. And the idea now is that we approximate this exact change with a linear approximation. And this linear approximation says, okay, how long is the time period? Okay, this is the first thing. And how does it change? How does it change evaluated at some point? So the exact change here on the left is approximated by a linearized version of the change. And here we look at the change, how do the variables of interest change, evaluated at this tau bar. And this tau bar is exactly that time period that lies in between tau k and tau k plus 1. So, and this is now supposed to approximate the exact change. And if we rewrite this problem, we arrive at the next line, where this is just by definition true, right? So we said y tilde k plus 1 is just our x evaluated at tau k plus 1, right? This is just by definition true. By the previous, here we see, in the previous slide, we see this is the definition of our yk. So this follows directly, and this psi here is basically also the derivative with respect to tau, evaluated at the average, the mid time point, and also the mid variable value. So this y bar here is what was the value of our variable of interest in the middle of the time period. And once we understand this is an approximation, every approximation makes an error. So we now, if we reshuffle a bit, we bring everything to one side, we get an error function. And this is the thing we want to minimize. So this down there is the thing we want to minimize. This needs to be sufficiently small for us to be satisfied. So to summarize now, what are we talking about? Here we have a description of the system of equations we're trying to solve. So for every time point we have given conditions. Here we have all the time points, so we have systems of equations for every time point. E0 here is a time point 0 at the beginning. The initial condition is to be met here, which is our b. Then in between we have our error functions that should be minimized. as well as possible stationary conditions. And in the endpoint, we have also possible stationary conditions as well as the final endpoint condition that is to be met. So now, understanding the system of equations we have here, we want to solve this. And since this is not possible without further ado, not analytically possible, we have to again linearize and iteratively solve. So if we say, okay, we want the solution of the system, we just say, okay, we want the solution of the system, this is this part, and then we linearize it around some initial guess. And this is now this y dagger. And this initial guess is, okay, what we think is, how the variables of interest change over time. And if we do this, we see that, okay, we get the starting point, so this is the level, this is the first order Taylor expansion of our system of equation, so our linearized system of equation. We evaluate it at the initial guess, plus, and this is now the change, the Jacobian of the system of equation with respect to the variables of interest, so with respect of y to y. So this is how the system changes if you deviate from the initial guess. So this delta y is how far are we away from our initial guess. And this now is a linear system which we can solve. Before we go into the Ramsey-Cass-Koopmans model and solve it with the relaxation algorithm, I thought I'm going to provide you with a small visualization of the Newton-Raphson method. Remember, we might end up with a highly nonlinear system, maybe also high dimensional, and we want to solve it. And this is often quite challenging, to say the least. But one thing we're really good at is solving linear systems, even in high dimensions. So the idea is that maybe if we have a nonlinear system and we want to solve it, maybe we can approximate it with a linear system. So, and the idea here is that we have to linearize the system somehow. Okay, and what do we need for a line? In the univariate case, it's easy. We need some point where the line goes through, and we need a slope. And the slope is typically obtained by taking the first derivative, because this provides you with the slope in this given point, right? So you need differentiable functions. Your system needs to be at least locally differentiable. So once you have your point, and the point, how do you get the point? Well, ideally you have an educated guess, but you could also just, guess somehow. The closer you are to the truth, the better. Okay, so in this case, in this visualization here, our initial guess is 0.7. And you see the linearization around, and we have this nonlinear function, the blue one, right? This is the solution we're after. The solution is here. The true solution is 1.4. So we want to find this. And if we linearize the system around our initial guess, it works quite well in some neighborhood, right? But the further we go away, the worse it gets. So maybe using a linearized version does not really cut it. But the idea of the Newton-Raphson method is now that, if we end up with a solution of the linearized system, what if we just take this solution and evaluate our system and our slope at this new solution? In the ideal case, if we are already in the slope, in the solution rather, then nothing would change. But if we just take our approximated solution and plug it in as the new initial guess and linearize around this new initial guess, you visually see already that the new solution suggested in the second round is much closer to the true solution. And if we do this a couple of times, now we plug it in again, linearize the system around this new solution, we are already quite good. And now the question is, how precise do you want to be? Well, because the more often you do it, the closer you get. And here you are already in the really small territory. If you do it once more, I guess, yeah, we're probably close to machine error, you know. In almost every application, this is good enough. And you see, maybe linearizing the system in the first run didn't really provide us with a good solution, but iteratively linearizing helps us find the true solution. And this is of course, a toy example, right? It gets a bit difficult to visualize in high dimensions, but I hope you now have a good intuition on how this works.